Let's review some of the main ideas from the motion detector lab. We have several graphs presented here, and the key thing to notice is what kind of graph they are. They're position graphs, x in meters. The first graph, how would we move to produce this graph? And we would stand still to produce a graph where we stay at the same x position as time increases. And so this would be D, stand still. Graph 2, we're not standing still now. We start out at some initial x and increase our x position, so we're moving away from the detector. And then now we're going back toward the detector. And so we'd move away, and here we're changing direction, turning around probably. And so B would be the best answer here. For graph 3, we're starting out at some initial position x and moving away from the detector like the start of graph 2. What's different here is the slope of the graph is changing. It's getting steeper. Here at the end, if you draw a tangent line, it has a certain slope. Compare that with a tangent line toward the beginning. It has less slope, and so the slope is increasing, the speed is increasing as we move away from the detector. Notice they're all positive slopes. And then in graph 4, we start out moving away from the detector, but now the slope is decreasing, approaching 0, and so in graph 4, we are slowing down. And so we are speeding up for graph 3 and slowing down for graph 4. Now the same question, the key thing again to notice is this is a velocity graph. On quiz questions, the most likely reason for you to make mistakes is to answer thinking it's a velocity graph when it's a position graph and vice versa. Always look at what's on the y-axis and the x-axis for that matter. And so graph 1, we're not standing still since this is a velocity graph and we're above 0. We have a positive velocity, so we're moving away from the detector at a very steady rate. And graph 2 is similar, except now we're moving toward the detector because we're below 0. We have a negative velocity. For graph 3, you might think we're walking away and then turning around and coming back, and that would be true if this was position, but it's not. It's a velocity graph. And so our velocity starts at 0. We're speeding up, and then at this point we don't turn around. We still have a positive velocity. We're still going away from the detector. We're just slowing back down. And for graph 4, we're starting out with a positive velocity and we're slowing down to 0. And then what do we do after 0? Now we have a negative velocity, and so we're heading back toward the detector. And so what did we do at this point? We reversed direction, or we turned around. So a velocity graph looks very different from the position graph for turning around. Keep these separate. These came right from the homework. I'll just go over it quickly. When we're talking about speed, we're talking about the magnitude of the slope, how steep a position graph is. These are all position graphs. And so in the first case, the A line is steeper than the B line, and so it's moving with the greatest speed. In the second case, these are supposed to be a tie, and so they're both going the same. The downward slope here is the same in magnitude or value as the upward positive slope of A. In graph 3, you should be able to tell that line B has a steeper slope, and so it has a greater speed. Line A, less of a slope, so less speed. Line A would have a positive velocity and B a negative velocity, but again, we're asking about speed. And then finally here, even though A is way up here, its slope is 0, so it has 0 speed. B is going faster. This is similar, except now we're looking at a velocity graph. And so if you look at any given time t, the line that's the highest up is the one with the greatest speed in this case, since they're both above 0. And so A always has the higher speed. I guess you could say maybe at time 0 they're both going the same there. And so in general, line A is the best answer here. And then now we're looking at a velocity graph and which object is moving faster, and again we can see that changes over time. And so at first line A is going faster, at some time later line B. And so first A, then line B. Which object is ahead? You have to watch about this. Even though A is going back toward the origin, you can't tell because you don't know where it started. And so A could have started way far in the positive direction from the origin. And so it could still be ahead of B even though it's going back toward the origin. The intersection just represents at that time t, they both have the same velocity. An important skill from the lab is being able to create a velocity graph given a position graph. And the key relationship is that velocity is the slope of the position graph. And we have two different slopes on this position graph, so we need to know what each of them is. And to calculate a slope, you need 2 points on the line. If you're used to picking 1 point on the line, you're going to have trouble in this class. And so 2 points on the line, I usually pick them fairly far apart. And so this first point here is x equal 0.5, y equals 1. And the second point, x equals 3, and y equals 3.5. And so the slope is the change in the y, or a little confusing here, change in position or change in x, over the change in x, which is time. And so 3.5 minus 1 is the change in position. 3 minus 0.5 is the change in time, and this is in meters and seconds. And so you get 2.5 over 2.5, or 1 meter per second. And the final part here, the slope is 0, so the velocity is 0. So we have a 1 meter per second velocity about for the first 3 seconds, and then it drops to 0. It wouldn't drop instantly. If this was somebody walking, you'd have to have some sort of curve here, but we can idealize the graph and show a vertical line, and then it stays at 0. Another skill is doing the reverse. If we start with velocity, how do we get position? And we already mentioned this. You have to be given the starting point. The velocity graph doesn't tell you where the object started. And so we're starting at 1 meter, and so the question is, where do we go from there? Well, you can see in the first 3 seconds, we're not going anywhere. And so the velocity is 0 for the first 3 seconds, so the line is at 0. How far do you go from 3 to 6 seconds? From here to here. You could use our average velocity equation. Average velocity is the change in position over the change in time. And so the change in position is the average velocity times the time. And in this case, the average velocity is 0.5 meters per second. And the time is 3 seconds. And so you get 1.5 meters. And what would that look like? Well, we started out at 1 meter, and we added 1.5 meters to that. So now we're at about 2.5 meters. How about for the next 3 seconds? Well, we start out at 6 seconds at negative 1/2 meter per second, and we maintain that for the next 3 seconds. So using the same equation, the change in position is the average velocity, in this case negative 0.5 meters per second, times the time, 3 seconds. So you get negative 1.5 meters, and so that is going back to where we started, so we'll end up here. And pretty straight, you know, if you're walking, it's going to be a little wiggle to it. And then what does it do next? Well, now we've stopped, and so we have a horizontal line. One thing you have to watch is the difference between average speed and average velocity. It's not a big deal, but you will get asked questions like this. and the average speed is the total distance covered. If you're wearing a pedometer, it would have measured that 1.5 meters walking away, that 1.5 meters walking back, and so you went a total of 3 meters in 6 seconds. Your average speed is 0.5 meters per second. Average velocity is your displacement over the time. And so you went 1.5 meters away and 1.5 back, your displacement is 0. You ended up back where you started, and so your average velocity is 0. Now there's another way to think about doing this operation, going from velocity to position, and that is using the idea of area under the velocity graph is the displacement. Why do I have under in quotes? Because sometimes it's the area over the velocity graph, as we'll see. And so we know we didn't go anywhere the first 3 seconds. Then the next 3 seconds I have a rectangle, and the area between the curve and the x-axis represents our displacement in that period. And so this is an area like buying carpeting and square footage. This is area using the units of your graph, meters per second, and time axis down here in seconds. And so the height of this rectangle is 0.5 meters per second. The width is 3 seconds. The area is 1.5 meters, and that's how far we went. This next part, the area between the curve and the x-axis, so you can see it's the area above the line, although they usually just say area under. So this is going to be a negative area, kind of a strange idea, but that's what it is. And so the height is negative 1.5 meters per second. The width is 3 seconds. The displacement, negative 1.5. And we can continue with the graph. You may find this a little strange, but the idea of this area, it always works. Average velocity only works if our velocity is changing at a constant rate, or otherwise constant acceleration. Area under the velocity graph is always the displacement. This will become important later on in the class. Let's see it used for a little more complex motion. How about the velocity starting out at 0, increasing at a constant rate to positive 0.5, remaining there, and then dropping to 0 at the end. What would the position graph look like here? Well, let's assume we're going to start at 0. And so we have our initial position at 0. And so this first part, you could use the average velocity, or you can get the area under the curve. And so the area of this part under the curve is a triangle. And so it's 1/2 the base times the height. The base is 4 seconds. The height is 0.5 meters per second. And so you went a total of 1 meter. And so in that first 4 seconds, you're at the 1 meter point. And notice, since the slope of position is velocity, notice the slope going up slightly as we speed up during this interval from 0 to 0.5 meters per second. The next part, we just have a rectangle here. And so the base is 4 seconds. You have to be careful with that. The base is not 8 seconds. It starts at 4 and ends at 8. And so the change in time, the base is 4 seconds, height 0.5, and so the displacement 2 meters. So we started at about 1, and at the end of 8 seconds, we're at about 8. At 8 seconds, we're at about 3 meters. And then finally, this last part, another triangle. The base is 2 seconds, the height 0.5, and so we end up going a 1/2 meter. And so we're slowing down. So we start out at 3, we end up at 3.5, and the slope is getting less and less as we go. You could also use the average velocity equation, where change in position is the average velocity times the change in time, but we need a new average velocity equation here, where this is just like averaging two numbers together. The initial velocity, v0, plus the final velocity over 2. Just like averaging bowling scores. You bowl 100, then you bowl 200. The average is 150. 100 plus 200 divided by 2. And so you can get the average velocity for this first part of the motion. It's the initial 0 plus the final 0.5 over 2, or 0.25, times 4 seconds, 1 meter displacement, just like we got from the area. This part, the average velocity is just a ½ meter per second. It's not changing. You don't really need to do this part. So you end up again going 2 meters. And finally, this last part, your initial velocity is 0.5. Your final is 0 over 2, 0.25 times 2 seconds. So you're going to go a ½ meter. Two different ways of doing the same thing. This way is perfectly fine, but remember the area idea always works. This only works if these are straight lines on the velocity graph. Let's look at a homework problem from Halliday, Resnick, Walker, 5th edition, Chapter 2, number 17. This concerns an armadillo walking back and forth. Maybe we have a motion sensor on it, but this armadillo can go behind the motion sensor. So let's imagine a number line. We could have drawn this on the floor during the motion detector lab. And there's x equals 0, and the armadillo can go out here in the positive x and over here in the negative x. So he's somehow getting behind the motion sensor, or we just made our origin maybe 2 or 3 meters out in front of the motion sensor. And so the first question, when, if ever, is the animal to the left of the origin on the axis? Well, here is the origin, and to the left of the origin means in the negative x. And so here's negative. Notice the x up here. Some students miss that. And so we start out negative x, crossing into the negative x at t equal 2, and we leave it at t equal 4. And so that would be d between t equal 2 and t equal 4. When, if ever, is the velocity negative? Remember, the slope of a position graph is velocity, so whenever the slope is negative, the velocity is negative. And we start out with a negative slope. It stays negative all the way to t equal 3, and then it goes positive. And so between 0 and t equal 3, D is the right answer. 3, when, if ever, is the velocity positive? Well, we just need to look where the slope is positive, and from 3 seconds all the way to the end, here it's 7 seconds, so this would be B. And when, if ever, is the velocity 0? Is the slope ever 0? Well, here I have a negative slope, and on the other side of t equal 3, I have a positive slope. And so the slope had to go through 0 at about t equal 3. If you draw a tangent to that point, you can see the slope of the tangent is 0, so the slope is 0 there, and so it's going to be at t equal 3. Let's look at another one from the book, very similar to these examples we've been doing. What is the total distance covered between 0 and 16 seconds by the runner whose velocity is shown above? This is a velocity graph, and so I want the area under the curve. You could do this with the average velocity technique. Here you start out at 0 and end up at 8, so the average velocity is 4 times 2 seconds. I'm going to do it with area though. And so we have the area of a triangle, and so it's 1/2 the base, 2 seconds, you want to be careful with that, times the height, 8. And so pretty easy to do. You can do this in your head. 8 meters is the area of that first piece. Then I have this rectangle or square, depending on how you graph this. And so the base here is not 10 seconds, right? It's from 2 to 10. And so the base is 8 seconds, and the height is 8 meters per second. And so it's 64 meters for that part. Now you have a trapezoid, or if you want, you have a triangle and a rectangle. But a trapezoid, the area is the average of its heights. And so that'd be 1/2 8 plus 4. You can see I'm getting average velocity there too. And then the base times the base, which is 2. And so 8 plus 4 is 12, over 2 is 6, times 2. So we get another 12 meters there. And finally, this last rectangle, we have a base of 4 and a height of 4. And so that's 16 meters. And so let's add all these up. We have 8 plus 64 plus 12 plus 16, and if you get out your calculator, no, you don't need your calculator, you'll find out that comes out to 100 meters, and so that would be C. An alternative way to do this one is to figure out what the area of one square is. So let's look at that. One square has a height of 2 meters per second and a width of 2 seconds. So each square represents 4 meters. So you can count all the squares and multiply by 4. And so here we have 4, 5, 6, 2 cut in half, 7, plus 4 times 4, 16, that's 23, plus 4 cut in half, 25, times 4, 100. And so try that one out, counting the squares, both are okay. That's the end of this review.